Rihards Gailitis. I'm a PhD student at Technical University, and I'm going to talk about plain geopolymer concrete cross-section surface create and shrinkage tests in compression and tension. The main aims of this research or study was to determine the effects on the specimen microstructure after.
I'm just taking 1 second because I think you have a window in front of your slides, maybe. We can see a dark, I guess I'm not the only one who can see it. Sorry.
Anyway, as I was saying, the aim of this research was to determine the microstructure differences of the creep and shrinkage tests in compression and tension, and to determine whether or not the differences that would be visible or not visible bear any fruit on the creep strains in general, and also to determine the effect on geopolymer concrete at the early age testing, and further deduce whether or not there are some links between the microstructure and the long-term properties of geopolymer. So geopolymer, some authors claim that it's the cement of 21st century. Basically, it's a three-dimensional material, binder material, that is based on silicon and aluminium reactions, and they are by hydrogen. Basically, how the geopolymer is called is low calcium alkali activated binder. So main point of using geopolymer basically is environmental benefits. First of all, it's made by using industrial waste materials such as fly ash, various slags, etc. And also as the main material to get this powder binder level doesn't need any excess heat in making of it and getting its properties. As for the Portland cement, the CO2 drastically reduced in this process. Some authors using geopolymer concrete as building material, the CO2 emissions in making elements can be reduced up to 6 times. As for the long-term properties, such as shrinkage, I'm guessing that most of you know that for the first 10 years after the structure is made, the main creep and shrinkage take their place on them. So, and also as for the tension tests for long-term properties, as Portland cement-based composites, also geopolymer based composites have significantly lower tensile strength and compressive strength. Therefore, even if the element that is tested is made quite thick, it's still quite brittle, and if it isn't handled as well as it should be, so it can develop some unwanted cracks, and therefore the test is ruined. So for the testing purposes, cylindrical and cube-shaped kind of were made. The cylinders were cut and grinded to a height of 190 millimeters, and the cubes were cut into tile-shaped specimens with thickness of 15 millimeters. And also I have to mention that all of this to scientific organizations in Riga Technical University and in Krakow University of Technology. This part was done in Poland. So long-term tests took place in Riga Technical University. Creep was tested in the Liber test stands, as you can see in the upper images. on the right, you can see the schemes for these lever test stands, and shrinkage strains were measured in specific test stands. And both creep and shrinkage tests were done simultaneously at the same environment, in the same room, so that furthermore, the results for these tests could be used together, and the data analysis would be done much more thoroughly. So when the long-term tests were done, the sample preparation for the microanalysis tests were begun. Quite easy procedure. The necessary sections of the creep and shrinkage specimens were saturated with the polyester resin to prevent any influence on element microstructure during the cutting and drilling processes to extract the samples out of the creep specimens and shrinkage specimens. When the cutting and drilling was done, basically that's for the cutted samples, the surface was evaluated, and if the sample didn't have a surface thoroughly saturated with the polyester resin, it was done once again to prevent in the polishing parts that some unwanted cracks would be developed that otherwise wasn't there in the pre-testing part. And afterwards, the excess resin from the surface were grinded and polished off, so that at the end we have a polished section that has its pores filled and cracks with the resin, but the binder and the filler part is just polished and no other materials are on top of it. So for the microanalysis was done in the scanning electron microscope. For the tests in microscope, the samples were plated with gold, so that the plating was done much more evenly. The samples had copper strip added to them, and after the plating procedure, the specific zones, as you can see on the bottom part of images, were put it onto the specimens so that it would be much more easier to track inside microscope where are the specific areas that are wanted to be images taken of. So for the samples that was taken from the cylindrical specimens, there were 5 specific added. Each of the zone was 10 by 10 millimeters. And as for the tension tested specimens, they had this zone 10 by 20 millimeters in just one piece of the zone, and it was placed at the base of the notch that is for the computation specimens. So each of the zones for the samples from the compression specimens holds some 24 to 28 images, and for the tension samples, the amount of images are 46 to 54. So basically, it depends on the amount of the cross-layer part that is necessary so that the images can be added specifically in the right order at the right place. So image compilation was done in the Adobe Photoshop. Also, the dividing into layers and the RGB code allocation also was done there, and the amount of each of the layer pixels was counted also by using Adobe Photoshop options. So the results, as you can see on the left-hand side graph, that the compression specimens show significantly higher creep strains than the compact tension specimens, approximately 46% more. But I actually have to say that because these are two different stress strain states, it's not quite correct to evaluate the creep and as well strains in this way. So on the right hand side, you can see here these curves that represent the specific creep, or in other words, the actual creep strength divided by the average compressive or tensile strength of the values that were determined prior to the testing. And we can see here that actually the specific for the compact tension specimens are significant, and the compressive specimens more than 7 times. So it kind of leads that not only as the tensile strength is lower for the geopolymer, but also inside microstructure, there are something happening that would encourage these significantly higher strains to happen. So further analyzing the amounts from the surface analysis of the polished sections, we can see that for the compact tension specimens, there are significantly high amounts of air voids in the specimens, on average 24 to 32% higher than cylindrical shaped specimens. Furthermore, it said that for the cylinder specimens were used for the compression tests, this amount filled the data with the filler. So in conclusions, there will be the answers, possible answers obtained. So further analyzing the polished sections of the tension specimens, we can see here, this is the notch base or the beginning of the notch of the compact tension specimen, that for them there are significant amount of microcracks in them, and most of these microcracks goes from one pore to another, and then makes a kind of significant mesh in there. And it's not only for the ones that were tested for creep, but also the ones for the shrinkage. So this leads to thinking that because of the early age testing, the shrinkage plays a huge role here, the microcrack development, and therefore the loss of tensile strength. So further analyzing the notch area, we can determine that for the creep specimens, there are significantly larger area of the notch. It's 5.7%, but even more if we measure the opening of the notch at the beginning of the polished section. We can see that the notch opening there is 28.11% larger than the shrinkage specimens. So we're thinking that, yeah, there are, after creep test, there's significant amount of the deformation that has happened that doesn't, that is not elastic. So for the conclusions here, we can conclude from these tests that compact tension specimens have significantly higher amount than cylinder type specimens, that leads to think that cube shaped as a base of the computation specimen making form airvoid wise is not quite good, because even though the samples, when they were made into the cubes, they were vibrated, not all of the air can escape in the vibrating process, and a significant amount of air still remains there. Also, that creep strain amount for the compression specimens is 35.8% higher than the creep strain tension. But in contrast here, the ultimate load values, and I want to downline ultimate load values here, for the compression specimens is 99.54% higher than the tension specimens. And this leads to the next conclusion: the specific creep for the specimens in compression is on average 85.92% less than computation specimens. Therefore, in tension, geopolymer composite shows 7.5% larger creep impact than in compression. And from the creep and shrink curves and the notch base part crack analysis, it is really apparent that tension specimens, in this case computation specimens, have lower elastic strain path, and in early stages it develops unwanted microcracks in the notch base, and therefore tension and elastic strains at the beginning of the tests are on average 90% less than compression specimens. Thank you for your attention.